Hi, it's Mr. Anderson, and in this video I'm going to talk about exponential growth, which is how populations can explode. Most students understand exponential growth, but the math sometimes gets a little tricky, and so I'm going to step you through that in a couple of ways. And so let's start with this rabbit right here. Let's say it's part of a population. We don't only have one rabbit, but we have a number of rabbits in our population. We refer to that in all of the equations as n. N is going to be the population size. Now that's going to change as we go through time. But this is going to be our original population, which is going to be n. And let's stack those rabbits up so we can count them. So our n to start is going to be 10. So we have 10 rabbits at time 0. Now that population is either going to increase, it's going to decrease, or it's going to stay the same. And what things are determining that? It's going to be our growth rate. And so this is the second letter you should remember, and that's R. R is going to refer to how much it's changing over time. And there's really only two things that are going to change that population. We're going to have new rabbits, that's going to be births, and then we're going to have dead rabbits, and that's going to be deaths. And so those two things are going to contribute to the change in the population, but it's a per capita. In other words, we have to divide by the n, which is going to be the original population size. And so let me make some baby rabbits. So if I click here, we've got 5 baby rabbits. And so our births would be 5. And then let's say I want to kill a couple of rabbits. Let's kill that guy. Don't worry, they're okay. They're just virtual rabbits. And so I kill that one as well. And so we've got births of 5. We've now got deaths of 2. And what was our n to begin with? It was 10. And so if we figure out our r value, that's going to be 5 minus 2 divided by 10, which is 3 over 10, which is going to be 0.3. And so our r value is 0.3, or our growth rate is 0.3. What does that really mean? It's the factor at which our population is increasing. And so if I take 10 times 0.3, I'm going to get 3. And that's how much our population increased. And one thing you should know about that growth rate is that if the ecosystem is stable, the growth rate is essentially going to stay the same. It's not going to change over time. And so you might think, well, if the growth rate stays the same, isn't the population just going to increase along a consistent amount? Not really. And so let's watch what happens. Now we're going to take 0.3 growth rate for the next generation, and we're going to, instead of multiplying it times 10, we now have to multiply it times 13. And if we do that, and we'll use this equation right here, this is the change in n or the change in t, we're going to take our growth rate, which is 0.3, and now multiply it times 13. Well, we don't get 3 anymore, we get 3.9. And so I'm going to round. That sounds a lot like 4 rabbits. So I'm going to add 4 rabbits. And now our population is up to 17. So even though r stayed the same, since we multiplied it times a larger value, we're going to get more rabbits in the next generation. So let's do generation 3. We're now taking 0.3 times 17, and I get 5.1, which is a lot like 5 rabbits, and I'm going to add those 2 rabbits. Or if we now multiply that growth rate times 22, I get 6.6, which is pretty close to 7 rabbits. So we're going to add those 7 rabbits. And so we now have got a population of 29. And so you can see that the population is increasing. But if I were to ask you a question, I could ask you some hard questions. The first one's not so hard. What's the population going to be in year 5? Well, to do that, you take 29 times 0.3, and then we'd add that to 29. But what if I asked you 10 or even 30? Well, this problem gets pretty hard, and so you're quickly going to want a little bit of help. And for me, when I want help, the first place I go to is to a spreadsheet. And let's go to the spreadsheet. So we're going to go to Excel, kind of remember those numbers there. And so let's kind of rebuild that chart. So on the left side, we're going to have 0 as our first time and 1 as our second time. If you didn't know how to do this in Excel, I can select both of those, grab this little corner here, and I can increase, and it'll do the counting for me. And so let's go up to population time 30. Okay, so I filled that in. Now what's our original population? That's going to be 10. So I'm going to just put that in to start with. Now what's the next population? So I'm going to put a formula in this box, and to do that I'm just going to put an equal sign. So I'm going to put an equal sign. You can see the formula right here. And so what did we do? Remember, we're going to take the original population, so let me click on that. So that's going to be 10. And then we're going to add that. To that, we're going to add our growth rate, which was 0.3 times, and then we're going to click on that again. And so let's see what we get. So we get 13. And so what we did is, again, we took what was in this cell and we added it to what was in this cell times 0.3. And so again, through the magic of a spreadsheet, I can simply grab this, and it's just going to use that same thing over and over. It's going to iterate on that. And so what we're going to get is it's going to do all of the math for us. And so what did we have in the first one? 13, 17, 22. This sounds familiar. Now, It's obviously not rounded off, and so this isn't the correct number of rabbits, but we see now this exponential curve here, or this J-shaped curve, or sometimes we call it like a hockey stick curve because it's quickly turning up like that. And so now we could quickly answer those questions. At time 5, we should have around 37 rabbits. What was the next one? I think 10, we should have around 138 rabbits. And if we go all the way down here to time 30, we're going to have 226,199 rabbits. So that's a lot of rabbits really, really quickly. And so you can see how exponential growth takes off. But what's fun about a spreadsheet is I could play around with it a little bit. Let's say instead of 0.3, if I change my growth rate to 0.1. So if I do that, what are we going to get? Well, if I move this all the way down again, we're going to get another J-shaped curve. Now, it's not going to be as steep as that one was, and we didn't have as many rabbits at the end, but we're still going to be exponential growth. Or if I were to go edit that variable again, let's make it 0. So let's say we take it times 0. What would we get then? Well, it's 10. In other words, if I go all the way down here, what are we going to get for a value? Well, we're not increasing at all, and so it's going to be 10. It's going to stay 10 the whole time. A really hard question that I ask the students is this. Let's say we get a negative growth rate. So let's make it negative 0.3. Well, what are we going to get for a value there? Well, we get 7 here. But if I go all the way down, what do we get? Oh, that's weird. We're going to approach kind of a limit. We're going to approach 0. And that's because we're going to take off larger amounts to begin with, and then we're going to take off less amounts as the population gets smaller and smaller and smaller. So again, that's spreadsheets, but you don't always have a spreadsheet with you. Sometimes you just need a calculator and a little bit of algebra. So let's go to the algebra. This is going to be the algebraic solution to this. And so we've got an equation for exponential growth. And so change in n over t is going to be equal to n, which is going to be our population size, times 1 plus r, where r is going to be the growth rate, and then we're going to raise that to t, where t is going to be equal to time. And so let's make sure that this works. Let's start right here with 0. And so let's plug in our numbers. So we're going to put 10 in here for n. That's that original population. 1, and then r is going to go right here. It's going to be 0.3, and then we raise it to the 0 power because our time is going to be 0. Well, if we simplify that a little bit, anything raised to the 0 power is always 1, and so that's going to be 10. And so that works out so far. But don't trust me. Let's keep going. Let's go to the next one. Let's go to 1. So if we now put in 1 for time, it's going to be, n is still 10. This is 1 plus r. Again, the r is not changing, but we're raising it to the 1 power. Anything raised to the first power is going to be itself. So it's going to be 1.3, and we get 13. Let's try that again with 2. So if we go to the second power, again, we plug in 2 here. It's the only thing that we're changing. So we get 1.3 to the second power. So we're going to have to square 1.3, which is 1.69, and we get 16.9, which is a lot like 17. Or I could just throw out another time. So let's say we go time 30. So then we're going to raise it to the 30th power. And so I get 26,199, which is going to match up exactly with our spreadsheet. We're going to have a lot of rabbits really, really quickly. And so that's kind of an algebraic solution. It's a quick way to be given a time and then figure out how much it's going to grow. And so a good question I could ask you is this. Let's look at bacteria rather than rabbits, okay? And so let's say we have one bacteria. E. coli can reproduce in about 20 minutes. In other words, one can make an exact copy of itself in about 20 minutes. And so let's say that none of them die. Let's say we get rid of the death rate. So we've got our births over n. And so how many births would we have? If we're just dividing in half, we're going to have one new E. coli. What was our original population? It was going to be 1 as well. And so now we're going to get an R of 1. And so instead of increasing by 0.3, we're now increasing by 1, which is really increasing by 100%. So we had one bacteria, and now we have 100% as many bacteria, or twice as many, or 100% in addition to that original. And so now we have 2. And so what are we going to have on the next round? We're going to have 4 and 8 and 16 and then 32. And you can see how exponential growth gives us a huge amount of bacteria really, really quickly. And so the question I might ask is the sky the limit? And so if we're looking at exponential growth, after 20 rounds like this, we're going to be way up in here. I can't even read this, 5 million, something like that. And so does it just keep going and going and going? No, because what I told you is kind of a lie. R is not going to stay the same forever. As it starts to grow, they're going to run out of food, resources, space, and so our R is going to start to change. And so then we're going to start to move into what's called logistic growth. And that's going to be a totally different set of equations, and I'm going to include that in another video. And so that's exponential growth, and I hope that was helpful.